Our guest, Dr. Krishnendu Guha. He is presently an assistant professor or lecturer in the School of Computer Science and Information Technology, University of College, Cork, Ireland. Prior to this, he was a postdoctoral research associate in University of Florida, USA. He was also associated with Intel India as a research fellow. Other than this, he held the position of an assistant professor in NIT Jamshedpur, India. He even served as a visiting scientist in ISI, Indian Statistical Institute, Kolkata, India. And he completed his PhD from University of Calcutta as an Inspire Fellow under the Department of Science and Technology, Government of India. He completed his MTech from University of Calcutta, where he secured a first class, first rank, and was the first and the university gold medalist. His research arena is essentially involved embedded systems, hardware security with focus on cloud and IoT platforms. He also has a strong interest in artificial intelligence and nature-inspired approaches. And that's it. Yep. Thank you, Guha, for the kind acceptance of our invitation, and platform is yours. Yeah.
Thanks. Thanks for giving my brief introduction. So, hi everybody. So, today I will be talking on this topic, that is securing neural network applications on hardware. So, as you know, this is basically a flavor mix of security and neural network, but it's basically focused on hardware. So, I will be starting with some key questions, and then I will be moving on to give some brief introduction on what is FPGA and ASIC, and then I will be showing what are the problems that are associated when we try to implement this embedded intelligence. And what is embedded intelligence? It is basically deploying our artificial intelligence and machine learning approaches that heavily depend on neural networks on hardware, right? So this is basically a brief overview of what I will be discussing today, and the talk is entitled as Securing Neural Network Applications on Hardware. So before I start, let me give a brief introduction of myself. So presently I am an assistant professor or lecturer in the School of Computer Science and Information Technology in University College Cork. It's in Ireland, and I am associated with all these things, that is the Science Foundation Ireland, SFI. So this is basically like our DST, that is the Department of Science and Technology in India. So in Ireland we have this SFI, that is Science Foundation Ireland, and this SFI has different centers for developing the science and technology in Ireland. So I am associated with this Connect Center and this Advanced CRT Center, right? So these are the SFI centers that are associated with development of technology, development of hardware, and all these things in Ireland. And in UCC, we have this NAS research and the UCC cybersecurity research, with which I am affiliated with, right? So in these centers, we do several works on networking, security, architecture, IoT, and everything. So you know today that we cannot focus on a single topic. We have to collaborate with others. We have to focus on multiple topics, and this helps us to broaden our research arenas. And this is the objective for developing all these small centers in UCC, that is the NAS research and the UCC cybersecurity research. So this, while this NAS research focuses on all this from networking, architecture, security, and all these things, we in particular, as I am a researcher in security, other than teaching the cybersecurity domain. So in cybersecurity, we focus on the software, hardware, cryptography, and all these things. So this UCC cybersecurity research focuses on specifically on security oriented research, and that not only involves only software security but also hardware security, which I lead. That is the hardware security in the cybersecurity research, and also on cryptography. And we presently focus on this post-quantum cryptography techniques. So if you are all interested in all these things, you can just ping me. I will be happy to connect with you all. And finally, these are my previous affiliations. So previously I was associated with University of Florida as a postdoctoral research associate. I was also associated with Intel India basically as a research fellow, and I taught for some time in NIT Jamshedpur, and I was a visiting scientist in Indian Statistical Institute, and in University of Calcutta I completed my M.Tech, PhD, and all these things as a Inspire Fellow under the Department of Science and Technology, Government of India, right? So this was my brief introduction, and now I will be moving directly into our present talk of today. So before I start with the present talk, let us focus on some key questions of today. So these questions will basically give you an overview of what we are or what are the challenges that we are facing at this present moment. So first one is that what can AI or ML learn from security, right? So we have this AI, that is artificial intelligence, ML, that is the machine learning, and this tries to mimic our human brain, where we deploy different types of neural networks and all these things, right? So what can AI or ML learn from security? So this is the first question. The second question is that what does security learn from AI or ML? So this is just the reverse. So if AI and ML have to learn from something from security, then security also needs to learn something from AI or ML. So what is it? So uh, and the third question is, what does security driven AI or ML look like? That is, first, what AI ML can learn from security. Secondly, what security can learn from AI and ML. And after each have learned something from the other, how we can mix them to, okay, how we can amalgate them to. So when we try to mix AI, ML and security together, we have this security driven AI and ML. And what does this security driven AI or ML look like, or what are the challenges that we face in deploying this security driven AI or ML? So this is our present focus, right? But if we have to understand what and how security driven AI or ML look like, we need to understand the first two questions, that is what AI or ML can learn from security, and the other way around, that is what security can learn from AI or ML, right? Okay. So now let's see AI, ML and security. So when this thing come about security, so how we can ensure security? So to deploy security, we need to think like the attacker, that is the adversary. We need to think how an adversary will think like. So before we can develop some security techniques, we must understand what can be the threats. And to understand what can be the threats, we need to think like an attacker, that how an attacker can attack a system, or what threats can be posed by an attacker. And after we learn this, then we deploy our security techniques, right? This a self-driving car. So presently we are trying to move and develop a self-driving car which where no drivers will be required, no manual drivers will be required. The cars can self-drive. We can just give the destination, and then we will just sit and relax in the car, and the car have all this AI techniques and AI techniques based on which it will perceive all the environment, all the traffic around itself, and the car will try to move to our destination. So this is our objective. But now, everything is not fine when we try to deploy the thing. So there can be several attackers. The attackers may try to hijack the car. So before we deploy this car, after we need to think what security mechanisms do we need to deploy it, and for that we need to think how an attacker can attack it. So an attacker will definitely try to hijack a self-driving car, and today it can be done by using AI, right? So we need to think how a self-driving car can be hijacked, and preferably by using AI, right? So let us think. First of all, what we can do is that we can basically put a wall, and in this in present scenario where all this AI and ML is involved, we can think of a virtual wall which we can put in. A virtual wall is not a realistic wall, but it can be like a um, like obstructing the sensors of the car. Okay, so next what we need to focus is that how we can attack the car sensors. That is, if we can attack the car sensors, then what will happen is that the self-driving car will not be able to perceive the environment around itself, right? So if the self-driving car will not be able to perceive the entire surroundings or environment, then it cannot work. Or we can also basically try to malfunction the sensors of the self-driving car. So if we can attack the car sensors, or if we can basically develop our AI or ML techniques in such a manner that the car sensors will malfunction, then the self-driving car will not work. Okay. And finally, this is quite interesting, put stop signs. What happens, in today in most of the first world countries, what happens is that they have all these electronic signs, right? So, and these electronic signs are basically generated by generative AI. Okay, now if these electronic signs can be changed, or can be changed at runtime by some attacker, then we can make the self-driving car stop, and if it can be stopped, then also it can be hijacked, right? So the important thing over here is this thing, security and AI ML. So in security, what we do is that we basically translate our intuitions into methodologies. So what is this? We basically try to foresee what can be the attacks, right? And if we can foresee what can be the attacks, then we basically deploy different types of mechanisms to protect us from these attacks. And these different types of mechanisms or methodologies that we develop are basically defined from our intuition, right? So security is essentially translating our intuition into methodologies. The second thing is AI or ML. This AI or ML is basically inferring. That is, we have our training data, and based on this training data, we can infer different types of parameters based on which we can work later, right? And now what we try to do is that we try to understand what is AI ML, we try to understand how security can be deployed, and then we try to mix AI ML and security, and then we have our security driven AI ML. Fine. Okay. So now let's think what AI can be in the presence of an attacker. So now we are trying to mix it up. Okay. So with the development of new technologies, adversaries tries to exploit it. So this is from ancient times. So whenever we develop some new technique, or we develop some new technologies, attackers tries to exploit them. Okay. So when we develop these www, that is world, that is the websites and all these things, attackers tries to hack the websites. Then we try to move over to these mobile platforms, and then the attackers tries to hijack our mobile platforms also. And now we are in the era of AI or ML, right? So in this AI or ML, the attackers also is trying to develop techniques where this AI or ML techniques can also malfunction. Okay. So, and this, the stake is even higher with AI, because AI is basically controlling more and more systems of our present day, and the attacker will have higher and higher incentives also, because when we basically use AI to predict, we basically use AI to formulate, we basically use AI to control, and all these things. So if this prediction, control, generation, all these things is controlled by AI, and if an attacker can basically hack the AI system, then it can basically change our predictions, then it can control our systems. So the stake is even higher with AI, because an attacker, and it is also seen in many cases that an attacker can easily basically poison the training data set, or the attacker can easily poison our AI or ML models, or even the attacker can steal the AI or the secrets of the AI or ML models that we will be discussing later in this talk. So as AI becomes more and more capable, what can be the things? The consequence of misuse by attacker will be more and more severe, right? So it all depends with how much function that we are trying to give AI. So more the control that we are trying to give to AI, the more the control that is going away from our manual control, and the more the things are going to the control of AI, the stake becomes more and more higher, because these are electronic things, these are computer programs, right? And if this and the stake is even higher when the attacker can basically control or seize the AI based programs, then the attacker will be more likely to attack our systems, right? So as AI becomes more and more capable, the consequence of the misuse by attacker will become more and more severe. Okay. So AI in the presence of attacker. Now we will be seeing basically some works of previous researchers of how these attacks have been done previously. So firstly, what is there is that it can attack a learning system, right? The learning system can be attacked, and how it can be attacked, it will not produce the intended or correct results. Normal learning, what happens is that we have a data set, right? And from that data set, the system tries to learn. We have a learning algorithm based on which a system learns, and then we develop a machine learning model. But now let's see, we can basically poison it. So we have this poisoning attack. So in poisoning attack, what is there? See, some data set is wrong, so we basically poison the data set. That is, we basically mix some malicious data in the data set, and if the learning algorithm will basically learn from this data set that contains some malicious data, then what will happen? That is the machine learning model that we will develop after learning will not work correctly, right? So the machine learning model will itself be malicious, because we have learned from our data set that contains some malicious data. So the machine learning model will not produce the intended or the correct results. Okay, so this is one type of attack. So the AI and ML, what will be our objective in future? The objective that we should focus in future is that the learning algorithms should be capable to understand that what the data set is, or whether the data set comprises all correct data, or the data set comprises some of malicious data. And if the data set comprises some malicious data, then how we can basically filter the data set, and we can only learn from the actual data and not the malicious data, right? So this is one arena of research that is being heavily deployed. That is how the learning algorithm is to distinguish between correct data and malicious data for a given data set. Okay. Now the second one is that it can cause the learning system to produce a targeted outcome that is designed by an attacker. Okay, so this is basically work done in UC Berkeley, right? So this work is done for generative models. So see the picture. First you have some original images, and from the original images you need to reconstruct them, and you will be getting some results like as it has been shown. But what an attacker can do is that the attacker can set up some target image, right? So see now the second case where there are adversarial examples. The adversarial examples is quite similar to the original examples, but the result is different. The result is that, see, all the targeted images are obtained instead of the reconstructed original images. So this is basically a targeted outcome which is designed by an attacker. So it also causes a learning system. It basically affects the learning system, right? So what should be our projected goal over here? Our projected goal over here is that we need to understand where the learning system is affected. So over here the data set is correct, right? So previously in the first example, the data set was wrong. Our learning algorithm have to distinguish which one or which data is basically correct and which data is basically associated with malicious elements, right? But over in the second case, what happens is that our data set is entirely correct, but our learning algorithm is affected by malicious elements or attackers, right? So in our second example, the attack position is basically the learning algorithm. Now if the learning algorithm is incorrect, then the machine learning model that will be developed will generate wrong result, which is in the second case. That is, see, the targeted images are basically affected, and again we get some targeted outcome. Now we are getting, definitely we are getting the wrong results, but along with the wrong results we are getting the targeted outcome. So this thing is basically associated with different types of real world scenarios. For example, in the traffic and everything, now if the traffic is AI driven, then if there is some particular green signal, an attacker may always try to make it red. So if the red signal comes from all directions, then what will happen is that a traffic jam will be a chaos. So this is a targeted outcome in a real world scenario. And the final one is about the data leaks. So the third attack can be to learn sensitive information. So what are the sensitive information over here? So we have this machine learning model, right? So this machine learning model has several weights, have several biases, have several coefficients based on which this is custom developed for some particular application. Now if the weights, bias, coefficients, all these are leaked, then what will happen? Then the adversary will try to reconstruct the machine learning model and try to develop them at a very low cost. Okay, so what happens is that a lot of significant amount of time, a lot of significant amount of effort, a lot of significant amount of expertise is invested in developing a machine learning model, right? So this machine learning model is associated with collection of several data sets. Then it is associated with significant amount of training. It is associated with significant amount of refinement, and finally a machine learning model is developed. And this machine learning model, if somebody can reconstruct the machine learning model, then then that adversary does not need to put all a significant amount of time, training, refinement, cost, expertise, all these things. So the model he can basically reconstruct with cheap amount of money. So we do not want this. So this AI data leaks is very important. And how this data leaks can take place? This data leaks can basically take place via some side channel analysis. It can be based on the parameter timing, it can be based on the parameter power, it can be even be based on the parameter leakage current. So what the adversary does is that the adversary tries to monitor all these side channel parameters like timing, like power, like leakage current, and all these things, and tries to reconstruct the actual machine learning model based on these significant parameters, right? The solution, what is the solution? The solution is that we need security in AI or ML. So when we are developing all these techniques, we need to put security. So see over here in this slide, I have tried to show that what are the most important attacks from the AI perspective. The first one is that the attack on the data set, that is how the data set can be poisoned. And if the data set is poisoned, then the learning algorithm cannot do anything in naive technologies until and unless we put security in it. And we must ensure security driven learning in the first case, so that the learning can ensure what type of data it is learning from, whether it is learning from correct data or it is learning from malicious data. And in that case, it should also try to filter out all the malicious data and learn correctly from the correct data of the data set. So, and in the second case, it is a targeted outcome. So over here, the data set is not attacked, but the learning algorithm is attacked. And therefore, security must be provided either in the machine learning model that is being finally developed, or when we are, or in the mechanism or in the architecture of the learning algorithm, where we can definitely put for some self-learning mechanisms, like we have our built-in self-test and all these things, right? So we have our beast and all these things where we can put this. And finally, the attack takes place in the third case, that is the sensitive information is learned via side channel analysis, that is after the machine learning model is developed, that is after we deploy the machine learning model, then from there how an adversary can recreate the machine learning model without investing significant amount of time, significant amount of money and all these things. And for that we need to prevent the data leaks. And how we can prevent the data leaks? We can prevent the data leaks via performing accurate synchronization where the timing channels are aligned. Then we can minimize the power. We can basically put some confusion approaches where an adversary cannot understand what actually the functions that is being developed. And for that, in hardware we have several techniques like obfuscation. We can we have also the confusion type of approach, and we also have the synchronization type of approach, which basically prevents the data leaks, right, in hardware. Okay, now we focus on how this AI can be misused. So for AI cyber attacks, there are like three common types. The first one is the AI model theft. This is what I was discussing in our previous slide. And in AI model theft, what happens is that the reverse engineering or hijacking of AI models takes place. And this hijacking of AI models takes place via learning, okay, via understanding the basic side channel parameters like timing, power and all these things. Based on this timing, power and all these things, the adversary tries to understand what are the weights, what are the biases, what are the coefficients of the model. And even via these timing parameters or power parameters, and there is also another parameter, that is the memory read or write. So how much amount of memory read or write takes place, or what is the timing of the memory reads and writes, an entire machine learning model can be reconstructed, right? So this is the reverse engineering that can take place to basically reconstruct or redevelop an AI model or AI model, right? So this is the AI model theft. Now the second one is the adversarial samples. In adversarial samples, what happens is that it introduces bad data samples to manipulate model classifiers. So this is what I was talking about in our previous slide. And finally, the training data poisoning. So it basically manipulates the data that trains the model. Okay, so this was the data poisoning that I was talking about. And for all these things, the security have to be incorporated, and security needs to be incorporated at all the levels. From the if we can put security in the learning algorithm, then we need to put security in the AI or ML model and all these things. So in each and every step, we need to put security techniques so that the AI model that is developed is foolproof, and this AI model can be prevented from different types of attacks, right? So this is a practical example of how this AI can be misused to attack other systems. For example, we have our training data, okay. So initially our training data is perfect. So this training data is not only used for training one system, but for training many other systems, right? But nowadays what we try to do is that we try to update our training data based on the models that we have developed, right? So for example, from the training data, we have developed a machine learning model, right? Now what the adversary does is that from the data that the machine learning model, this machine learning model basically creates more data, which are again added to the training data set, okay? So this is basically a continuous loop that takes place. Now what an adversary does is that the adversary manipulates the results that are obtained from the machine learning model which are inserted into the training dataset. So when the adversary comes in the loop and the adversary extracts the inference data from the machine learning model which are again put to the training data, then it actually poisons the training data. And when it poisons the training data, not only this model but also other models that are basically trained from this training data are also affected. So this is a practical misuse of AI, where from the training data we basically develop a machine learning model, and the outputs of this machine learning model are also used for updating the training data. And when an adversary comes in the loop, what the adversary does is that the adversary basically manipulates the inference data, and this manipulated data is again put into the training dataset, and this training dataset, when used in other machine learning models for training and for development and all these things, this basically creates wrong machine learning. So this is where we need to put security. So this is a practical, very practical example of how this security have to be enforced. Okay, so what is the process? So in everything we need a flow. We need to understand how we need to prevent this misuse of AI. So the process is, the first step is to find what are the vulnerabilities. So when we have developed a system or anything, we need to find what are the key positions of attacks, right? So we need to understand what are the points of vulnerability or how a system can be attacked by the attackers. So essentially what we need to do is that we need to try to find the loopholes in our system. So when we develop our system, the designers have to understand that what are the weak points in the system and what are the strong points in the system. So if we can understand the weak positions in the system, then we need to put different security techniques to ensure it. So firstly, we need to understand the design, then understand what are the weak points of the design via which an attacker can basically act, right? Secondly, we need to target these vulnerabilities. That is, we need to find out what are the weak points and how these weak points can be attacked. So how we can target these vulnerabilities. And finally, we need to attack these vulnerabilities. So then we need to understand, or again, that first slide of mine, where I showed you that intuition. So we need to understand, okay, then an attacker can attack this point of vulnerability, but how an attacker can manipulate it, right? So the three steps. So we need to find the vulnerabilities, then we have to we need to find the vulnerabilities, that is, we have to find the weak points in our design. Then we have to target the vulnerabilities, that is, we have to understand how the weak points can be attacked. And finally, we need to think of the mechanisms in which the vulnerabilities can be attacked, right? So from the security perspective, we need to think like an attacker, as I have told before, and what an attacker will do, we need to do that to develop our security techniques, right? So find the vulnerabilities or the point of vulnerabilities, then think out how the vulnerabilities can be attacked, and then finally what are the mechanisms in which the vulnerabilities can be exploited, right? Okay. So this is another way in which the malware can be put inside image classifier neural network. So see over here, so the first step is basically we design the network, then we basically train the network, right? Now what it happens is that the attacker can find the weak points and embed malware into the model. Then evaluate the model and do all this training, retraining and everything, and then after evaluating the performance of the model, then the model is basically published, right? And when this model is basically published with the malicious data, then the model is received with the malicious data, then the attacker may extract the embedded malware, check the integrity of the system, because the model will not perform perfectly, right, and execute the malware. Now there is a twist over here. So what is the twist? The twist over here is that the design of the network is perfect, then the training of the network is also perfect. So how we are basically putting the malware inside the model? So the twist over here is that in a neural network architecture, there are several layers of operation. Okay, so there are several neurons and all these things, and all the neurons are basically not used every time. Okay, so this is the point of vulnerability of a design that we need to analyze. We need to find out which neurons are not used, or which neurons are very less likely used. And in that points, we basically embed the malware. So we need to understand one thing in clear. That thing we need to understand is that the attack will take place, but the attack will not take place at every time. The attack will take place only at certain amount of time, at certain critical conditions, or the attack may take place like a time bomb, that is after some significant amount of time has passed, then only the attack can take place. So this is the point of vulnerability that we need to understand. Our system designer must understand in this particular case what the system designer must understand in this particular case which neurons are very less likely used, right? So which neurons are very less likely used or use after a significant amount of time frame, so that during the training phase or during the initial phases of operation, the application works perfectly, but after the training, after significant amount of time, after the system is deployed and all the users are satisfied, okay, the system is performing perfectly, we can invest in this application and all these things, then the malware exhibits its actual character. So over here what we need to understand is that the weak points in a system design, the weak points are over here are the neurons that are very less likely used or used only a significant amount of time. So we put the malware in those places which are very less likely used and possibly not at all used during testing phases. Okay, and these neurons can act something like a time bomb, that is after a significant amount of time when this neuron will be active, will be used, then this malware will be activated, right? So this is the twist over here. So and our objective is to find all these vulnerable places and make these vulnerable places strong, right? So that over here what it should be done is that our training should focus each and every neuron, but not only the neurons that are used mostly. Okay, so this is the point of focus over here. So during the evaluation of the performance and these things, this malware will not be detected, fine, but after a significant amount of time when the model is actually working perfectly and some critical scenario occurs or some trigger occurs, that is the trigger can be external or internal. The external trigger can be like an adversary knows the time period or knows the particular condition at which the neuron can be activated, and the adversary basically activates it or puts the essential criteria. So this is like an external trigger, and this trigger can take place in hardware via some antenna or via some sensors, right? So this is an external trigger. And what can be an internal trigger? An internal trigger can be like a time bomb in hardware. So we basically have all these hardware trojans and all these things which I can discuss after this, but these are essentially internal triggers like a time bomb. So after significant amount of time has passed, after the training phase, after the initial working phase, and all the users are satisfied that okay, this model or this system is basically working perfectly, then with some external or internal trigger, this a particular neuron is activated, okay, that contains the malicious circuit, and then all the malicious results are generated, and if the results are used to update the training data set, then it becomes a a chain reaction where like the training data set is malfunction, the training data set is poison, and all the models that are learning from the training data set, those also will get poison, and machine learning model will generate some wrong results, right? So what we need to do over here from the security perspective, we need to test each and every neuron. Okay, it will be time consuming, and in today when there is quick time to market deliveries, all these time factors comes into issues. Okay, right? So due to that quick time to market deliveries and the stringent marketing deadlines which we all have, we do not focus on entire time for testing all the each and every part of a circuit or each or every neuron in a circuit, right? So we only test the major things, but this should not be done. And if also we cannot put this during the training, if we cannot put so much of time in the training, then definitely the designers have to put in some built-in self-test and all these things which will essentially test all the internal circuit and all these things, right? And after finding out the what are the key points, we need to extract the embedded malware, so that, and we need to check that okay, the malware cannot function anymore. For that, what we need to do is that we have to quarantine. So now in hardware we have different isolation and quarantine possibilities, where after we have detected that some part of the circuit is acting maliciously, so what we do is that we basically quarantine the circuit, or we basically isolate the circuit from the other places, right? So this is what we need to do, right? And now let me give you an example of an attack scenario which is done in some generative models. So this generative model is used as a compression scheme, and the attacker's goal over here is that to reconstruct a different image, right? So the decompressor will basically reconstruct a different image from that the compressor sees. For example, see in this diagram, the attacker tries to change the output. See over here, the compressor sees an input of 7, but after some operation takes place, the decompressor gives an output of 8, so which it should not be, right? So this is a practical adversarial scenario. This was again done in UC Berkeley. This work. Okay, now see some image classification tasks. See, this I have shown it before also. So this is basically a targeted outcome by the attacker. So this was done in UC Berkeley. So in this original images we have, and we need to reconstruct the images in our output, right? So this basically passes through an compression. So the original images are passed through a compression and finally decompressed into this output, and in the process is done essentially to reduce significant amount of power and all these things. But when this attacker attacks the system, what happens is that we get some targeted outcome, that is, see, all the images are changed into a particular target image, that is the 0 over here, right? So this is another example of this targeted outcome, right? See, there are several pictures, so these pictures have to be compressed and decompressed, and also some refinement is essentially expected into the outcome. So in the first layer, what you will see is the original image and the reconstruction of the original image, right? But what happens in the second case is that you have the same original image, but see, all the faces are same. That is, the targeted image is now the output is basically essentially contains all the targeted image, right? So this is a practical example of of how this AI model can be attacked, and we basically get a targeted outcome. Okay. Okay, now we are in the phase where we try to mix both of them, security driven AI or ML, right? So this is how we try to emphasize that how security driven AI or ML can take place. That is, the security will be incorporated, the different security elements will be incorporated in the AI or ML methodologies that we will develop. And how we can do so, that is, this AI or ML methodology have different neural network based architecture, and we need to secure this architecture, right? Okay, so how the security helps AI or ML? Firstly, it ensures integrity. So what is integrity of a system? That is, the system should produce correct result, right? So we need to incorporate security in the AI or ML algorithm or the design afterward that we get in hardware, so that it does not produce wrong results, right? So it should protect from the poisoning attack, it should protect from the targeted outcome attacks. Okay, so remember the slide that I showed you, the different types of AI attacks, the poisoning attacks and targeted outcome attacks, right? So this security must be enforced so that it ensures the integrity of the system from adversarial machine learning attacks, right? Secondly, it should ensure the confidentiality of the system. And what and how it can ensure the confidentiality of the system? By preventing the data leakage of user data. And also, when we are thinking of this AI ML model, we need to think that how these wastes and biases, all these things can be protected, right? So this is what we call privacy preserving machine learning. So this machine learning algorithms plays with a lot of user data, and even it stores user data into a repository, and also it also tries to infer from the user data and retrain the system. Even it tries to infer from the user data, and this thing is put into the training data set and all these things, right? So we have all this privacy. So if the AI or ML algorithm are designed in such a manner that it can leak user data, then it is affecting the privacy of the system, okay, the privacy of the users. So we need to develop some privacy preserving machine learning techniques where the user data will not be leaked out at any case. And moreover, we also need to ensure the security so that the AI or ML model can be secure. That is, the ways, bias and all these things based on which this AI or ML model is developed. This AI or ML model have to be secure, or else what the adversary can do is that the adversary can recreate another model, and it can intercept the user data during its transit, and then with the recreated model it can basically steal the user data, and this will also affect the privacy preserving machine learning, and it will also affect the privacy preserving machine learning, right? So this is what we need to focus. Firstly, to ensure the integrity of the system. Secondly, to ensure the confidentiality of the system, and also ensure the privacy of the users, right? And finally, the security should prevent the misuse of AI. Okay. Now, how AI can help the security applications. So it learns from the different types of attacks and prevents future attacks. So what AI does is that AI always tries to learn, right? So if we have a model that can learn what are the different types of attacks that have taken place, and then it can also predict that what can be the attacks that can take place in future. Okay, so firstly it can learn what different types of attacks or different types of threats have taken place. Then it can definitely ensure protection from the threats, and also it can think of different types of attacks that can take place in future and prevent those attacks. Firstly, learn from the attacks and tries to memorize what are the attacks that has taken place, so that if those attacks will take place in future, definitely it can protect them. And secondly, it can also predict some future attacks. And what happens in today's environment, in today we have our distributed systems where we have different nodes and all these things like a common IoT framework. And in today what we try to do, we try to do cognitive IoT, where different IoT nodes basically tries to communicate with each other and develop some amount of cognition, right? And so this nose, after learning something, tries to deploy or tries to send these learning things to other nodes so that each one can learn from his own experience and from the experience of others, and also generate some concrete security things in future. So for this, what we have this trustworthy AI. So this trustworthy AI essentially features three things. Firstly, the reliability of the system. Secondly, the resilience of the system, and thirdly, makes the system responsible. So when we tell that, okay, the system is reliable, so what do we mean? We mean that the system is robust, the system is accountable, the system is transparent. Okay, so this robustness, accountability, and transparency of the system, these three factors ensures that how a system can be reliable or how much a system is reliable based on the metrics of robustness, accountability, and transparency. Secondly, resilience of the system. What does resilience mean? That how much a system is safe from the attack, or how the system can secure us, or how the system can ensure privacy. So the three things: safety, security, privacy, this makes a system resilient. So in other way, we can tell that a system is resilient when the system focuses on these three basic parameters, that is the safety, security, and privacy, right? Thirdly, we need to understand how responsible is the system. So the responsibility of the system is associated again with three factors. Firstly, the fairness of a system. Secondly, how ethical is the system. And thirdly, how sustainable is the system. Okay, so this responsibility of the system, because today's applications deals with a lot of users, so the system have to be fair to each user. It should not be biased to a particular user, right? And then the system should be ethical. Okay, so ethics comes into a play into AI. So ethical AI we have. So when we are trying to develop a system, we must also ensure that when we are developing a system with AI, the ethics of the system is there. So a system needs to be fair with all its users. A system has to maintain its ethics. Okay, and also a system needs to be, yeah. Okay. Okay, and also a system needs to be sustainable, right? So the sustainability comes from the energy efficiency perspective and all these things. So when we are telling that we need to incorporate security into AI, and we are basically developing a security enabled AI system, we have to focus on this trustworthy AI. So, and in this trustworthy AI, what we have is that the reliability, resilience, and responsibility of a system. Okay, and reliability depends on robustness, accountability, and transparency of the system. Resilience depends on the safety, security, and the privacy of the system, that definitely it can provide to not only a single user but also to multiple users. And the responsibility of the system comes because it is not dealing with only a single user but with multiple users, where a system needs to be fair, it should not be biased, it should be ethical, and the system should be sustainable. That is, we can use the system for a long more time, right? Okay, now we focus on the security of learning system in three levels. So when we are mixing up this AI, ML, and security and developing a security driven AI system, then definitely we need to think of not only in one level but in three levels. So what are the three levels, right? The firstly is the software level, because we develop this AI or ML techniques firstly in software, and after we have developed this in software, we try to implement in hardware. And how we do this, I will be discussing this in detail in my next part of this talk. So firstly, when we are writing our codes, right, we need to be sure that the codes that we are writing is foolproof, because these codes are not just like 10 or 20 lines of codes. It contains of lakhs and lakhs of lines. Okay, And also this consists of several loops also, and some of these portions are not well documented also, and also there are several parts of a code which are not utilized many times, right? So firstly it should come in the software level, that what codes we are writing. So are these codes safe, or these codes have some point of vulnerability where an attacker can exploit. So this is the first level, that whenever we try to design an application, whenever we try to write some codes, okay, so we must be foolproof that the codes that we have written are does not consist of malicious purposes. And why is this important? Because we do not write the entire code from the scratch. We basically take the code from third party repositories, right? So we basically use the codes that are available in the internet. And even because as these codes are huge, we even do not go through each and every line of code. We just try to see, okay, this part of the code is functioning well, it's fine, I can use this. So we just do like this. We never go through the entire course that we have written. So this is one of the basic points where some vulnerability can be exploited. And even what we do today, we have this third party vendors who can basically supply the codes, right? And we never test the entire code that we are basically procuring from different third parties, and we integrate that code into our main model. And this also we use for patching also. That is, okay, one portion is not functioning, we can patch the system with this code. And this is the point where vulnerability can take place, because inside the code some malicious elements can be put by some attacker, right? So these malicious elements will try to understand the entire system when this additional code is integrated into the system. So the first level of security is the software level of security. We must be foolproof that what we have developed, the software that we have developed, the application, the intelligent application or the smart application with neural networks that we have developed is complete or is foolproof. Secondly, the learning level, that is the learning algorithm, that is the algorithm that essentially learns from the dataset, is foolproof. Okay, so firstly, the things that we have, the code that we have written. Secondly, the learning algorithm must try to understand that what it is learned is foolproof or not. That is the training data, that is the data set from which it is learning, whether it is foolproof or not, or whether the data set is being poisoned by some other sources, right? So the learning algorithm must be developed in such a manner that it can essentially understand, or it can essentially span, or it can even filter the learning elements, that is what it is learning. And it should learn the correct and it should learn from the correct data and not from the malicious or faulty data, right? And thirdly is the distributed level. So this is what I was talking about previously. So presently we have the Internet of Things, and there are several new things coming up, Internet of Everything. And also we have this artificial intelligence based Internet of Things, AI, IoT. Several things are coming up. So what are these things? These are essentially, what it is called is that we try to uh, decipher, or we try to infer at the thing level, that is in the device level, where what happens is that all the things or the devices tries to communicate with each other, and whatever one device have learned, it tries to transfer this thing to another device, and then it tries to develop some cognition based inferencing scheme, so that it does not have to go to the edge layer or the cloud layer. So in a typical scenario, what we have in the top part, we have the cloud, then we have the edge, and then we have the things. So in typical scenario, from the things, some decision is tried to made at the edge level or the cloud level, but now we are in a cognitive Internet of Things position, where all the devices can communicate with each other, and it can also transfer what it has learned. and so that the learning takes a lot less time, and not only the learning, the inferencing also takes a lot less time. And with all the intelligent gadgets and all these things that we are using in today's world, the cloud is basically under a heavy burden. So it can take a lot of time, but we need results instantaneously, right? And for that instantaneous results, we need decision at the thing level, and therefore this cognitive inferencing comes into effect. And over where we need security also, because for example, if one device or if a thing is compromised, then what will happen? The thing can send some malicious results or malicious inference to other things. Okay, so this other thing that is again trying to infer something based on the results of its fellow components, basically, then it will generate some wrong results. So over here at the distributed level also we need security, so that we need to understand that whatever cognition based decision making or cognition based inferencing that we are doing for a particular device, then that device is secure enough, and it can also filter out different types of malicious results that it is receiving from other places, right? Okay, so security of learning things is essentially in three levels. The first one is the software level, the second one is the learning level, and the third one is the distributed level. Fine. So what are the challenges that we face in the software level? Okay, the challenges that we face in the software level are essentially associated with wrong code writing, or we are associated with different types of third party elements that we procure from other places and we try to integrate, right? And these are definitely the challenges that this must be resolved at the software level. So to resolve these challenges, we have different types of defense technologies also. So essentially there are two ways of defense. One is the reactive defense and the other is the proactive defense. And this proactive defense is again divided into two parts. One is the bug finding and the other one is the securing by construction, right? So what is reactive defense? See, the name will only tell you that it is a reaction. As we have this action reaction, so also in the software level we have this reactive defense. That is, when an action by a malware will take place, then only the defense mechanism will be triggered, right? So these are quite low power consumption, these are quite low energy saving. So in this, what we do is that we basically develop our security mechanisms in the software level in such a manner that when only an attack takes place, then only the defense mechanism is activated as a reaction, right? Now for the proactive defense, see, the name will only tell you it is proactive. That is, it tries to defend itself before an attack takes place. So while we wait for an attack to take place, for the reactive defense to get activated, we do not wait for an attack for the proactive defense. We basically try to defend the system from the initial stages only. So how it is done? Firstly, this is a bug finding, and secondly, it is the securing by construction. So bug finding, what we do is that we try to search the entire code and try to find bugs. So before we basically deploy or a certain amount of code or a certain amount of patch into a system, what we try to do is that we basically try to scan the entire system and try to find the vulnerabilities or the bugs in the system. So definitely 100% bug finding method in a code is definitely accurate, but due to the strict time to marketing deadlines and all these things, we cannot do entire bug searching. So what we try to do is that we try to develop the proactive defense via construction. That is, as we have these Legos and all these things, or you can think that when a building is trying to be built, we basically put brick by brick to develop an entire building, right? So this is how we try to do a secure construction mechanism, okay? Okay, so this is the automatic malware detection and analysis technique. So see the different types of attacks that can take place in software, like the SQL injection, the phishing attacks, then the cryptojacking, ransomware. So all these types of attacks that take place. And mostly these attacks takes place at the software level. And for this we need all this reactive defense, and this proactive defense is definitely better. But this proactive defense is costly, is time consuming, and this security is always an add-on. It is an add-on to the time, it is an add-on to the energy, it is an add-on to the power, it is an add-on to the system resources and all these things. So definitely this proactive defense is basically better, but the problem is all these add-ons, and therefore we move to reactive defense. And but this reactive defense, though this reactive defense is low in resource, in time, in power, but the problem is the reactive defense only takes place when an attack takes place. And if a system has to learn, then initially it cannot defend itself. If a system has to learn, if only an attack has taken place previously or based on the previous types of attacks, then only the system can work. And therefore the best way is the proactive defense, that is the security via construction. That is one level we try to develop, we try to learn from that level, and then when we try to go to the next level, then we try to apply what we have learned from the previous level, and then deploy this learning in the next level, right? So this is automatic worm detection and signature patch duration. So this is also a work that is done in UC Berkeley. Okay, so where it tries to detect the worms, and it also tries to match the signatures and patch the patterns and all these things. Okay, so what we have to do is that we need to evaluate the system under different types of attacks and not just normal events. And for that we have different types of testing schemes. One of the testing schemes is the regression testing. So in regression testing, there are basically three phases. In the first phase, what we do is that we basically reset the entire system, and then we test, we do the regression test selection. That is, we select different test criteria and we then prioritize the test cases, right? And for the security testing, we have this vulnerability scanning, security scanning, penetration testing, risk assessment, security auditing, ethical hacking, posture assessment. So the key thing that you need to understand over here is that in regression testing is quite fast. But over here, what we do is that we prioritize different test cases. We do not test this elaborately. We do not test this line by line, right? But in security testing, we have, see over here, we have several aspects of testing. These features, this vulnerability, these features scanning, these features how penetration can be done, these features how risk assessment can be done, and also it involves auditing, security auditing, right? So this security testing is foolproof. Okay, so now let's see what is the difference between the regression testing and security testing in our traditional software system. So there are two parameters. The first one is the operation and the second one is the goal. For operation, for the parameter operation in regression testing, what we do is that we basically run the program on normal inputs. And in security testing, what we do is that we not only run the program on normal inputs, but also we try to develop some adversarial inputs on which we run the program. So we try to make the system foolproof. Okay, so along with the normal inputs, we develop abnormal or adversarial inputs. So if you remember, I told the security is developing mechanisms on our intuitions, right? So we think, okay, so we try to think like an adversary. Okay, so an attack can be made in this manner, an attack can be made in that manner. So this can be our abnormal inputs, this can be our adversarial inputs, and we try to test the system in that manner. And for the parameter goal, so what is our goal? For regression testing, we need to prevent the normal users from encountering any error. So this is basically a regression testing where where you know, all different types of faults can take place, different types of errors can take place, and we need to prevent the normal users from getting those. And in security testing, what we do is that we prevent the attackers from finding the exploitable errors. That is, we try to find what are the points of vulnerability, and we prevent the attackers from exploiting them. Okay, now the second phase, that is the challenges at the learning level. So we need to evaluate the system under adversarial attacks, not just normal attacks like the previous case. Okay, over here also we have this regression testing, we have this security testing. So let's see. So this regression testing versus the security testing for our learning system, and in this, see, now we have our learning system. So what are our parameters? The first parameter is training and the second parameter is testing. For the training parameter in our regression testing, what we do is that we basically train on noisy training data. And what we try to estimate, we try to estimate the resilience of the system, okay, against the noisy training inputs. And for security testing, we basically train on poison training data. We try to estimate what is the resiliency of the system for different poison training inputs, right? So this is the difference between regression testing and security testing at the learning level for the training parameter. That is, in regression, we try to train on the noisy training data and estimate the resiliency of the system for the noisy training inputs. And for the security testing, we train on poison training data and we try to estimate the resiliency against the poison training inputs, right? And the second parameter comes in the testing. So for regression testing, what we do is that we test on normal inputs. We estimate the generalization errors. And for the security testing, we test on abnormal or adversarial inputs and we try to estimate the resiliency against the adversarial inputs. So the key over here is that we try to develop different types of abnormal or adversarial types of inputs based on which we try to find the resiliency of the system and all these things, right? So now what we try to do at the learning level is that we also try to reason the complex and the non-symbolic programs, okay? So over here we do not have any precise specified objectives and goals. That is, we do not have anything precise. We need to figure out with time, and that is where the AI or ML comes into action. And also we do not have any good understanding of how a learning system works, right? And also the traditional symbolic reasoning techniques also do not apply in this case, okay? So this is where this is the challenge of our learning level. And for this, what we need to do is that we need to develop new architecture and approaches that have stronger generalization and security guarantees, right? So now finally, what are the challenges at the distributed level? So we have seen what are the challenges at the software level. We have seen what are the challenges at the learning level. But now we have to find out what are the challenges at the distributed level. So you know, in the distributed level, we have different things. These things basically communicates with each other, and for this communication and everything, we need some agents. We need some local agents that can make some local decision making, right? And we also need to know how good a decision is. So we have to understand, we have to make sure that the local decisions must be foolproof. If only the local decisions are foolproof, then only the global decision will be foolproof and will be cost effective, right? So we have the agents for each particular host of the system, and these agents tries to communicate with each other, okay? The decision making at the local level, if these are foolproof or this decision making at the local level is secure enough, then only we can ensure the security at the global level. So this is the challenge at the distributed level, where security should be not only in the local level but also in the global level. And the basic condition over here is that the agents must be working safe and securely. The agents must be able to detect if any malicious operation is being performed by his host, or the agent must be able to detect that whether his host is compromised or not. If his host is compromised, then it has to isolate the host. It have to tell the other agents, okay, his host is basically compromised. So the inferencing uh, or the or the results that it is being generated, this should not be taken into account for the inferencing that is being done by other local agents or at the global level, right? So for this decision making, see what happens is that there are four key factors. One is the planning, then is the organizing, then is the actuating, and then is the controlling. So this decision making at the local level is associated with all these four phases, and this should be not only done in the local level but also in the global level, right? Okay. So when and where is this machine learning applicable in security applications? So this learning is mostly needed when no precise formal property is present. For example, in the spam filtering, so we have all our emails and all these things, right? So in these emails we all use these spam filters. Now how does it work? Firstly, it tries to understand from the other, it tries to understand from its previous history that what is, that is, it tries to understand our preferences or what things are important with respect to what work we do. Based on this, it does this spam filtering, right? So this is a very practical example of machine learning for security. Okay. The second thing is fraud detection. So we need to understand how machine learning systems can reveal different types of scams. So you know we are all in this wave and everything where different types of attackers, different poses, different types of frauds in front of us, and this machine learning must be able to detect them. Okay, so another thing is the human versus bot. We need to understand, okay, now what applications we are using. Are these performed by humans or are these being generated by bots? Because you know these adversaries, what they do is that they develop several types of bots, and in this they implant different types of malware, right? So these are the places where this machine learning can be applied in security applications. Now we come to hardware. So what is the need of smart hardware? Okay, so we have undergone several industrial revolutions from industry 1.0 where there was mechanization, water and steam powers. Then we have this industry 2.0 where there was mass production, electric power, assembly line and all these things. Then we move to industry 3.0 where we have that computers. We have this automated productions. We have this electronics. Then we move to industry 4.0 where we have this cyber physical systems, this IoT, networking, machine learning, Internet of Things, artificial intelligence and all these things, right? We have the system on chips and all these things, and now we are in industry 5.0, and this industry 5.0 features human-centric operations. So we basically put humans into the loop. So see, in this previous, from industry 1.0 to industry 4.0, humans were not in the loop. It was only related to machines. It was only related to development of machines. But now humans are also in the loop. In industry 4.0, we try to develop different types of system on chips. We try to develop different types of electronics and all these things that can infer and decide. But now in industry 5.0, we need the human factor also. We need to understand what is the human perspective, or therefore we have this human robot collaboration. That is the systems we are trying to develop. We try to involve the humans with it, right? And for that we have these cognitive systems. We basically try to mimic the humans, and not only mimic the humans, we also try to take their opinion into consideration, right? So we develop different types of customizations and all these things. So we have this artificial intelligence, we have all this machine learning, and now these have to be added into the system on chip or into the hardware, right? And what we will get is the AI infused system on chip, which is actually called our smart hardware. So we need the smart hardware today for all this cognitive decision making and all these things, right? So what are the modern trends? You know, we have these embedded systems, and these embedded systems are applied in each and every gadget, smart gadget that we are using. So these are from the electronic tablets, books, in our televisions, in the aviation industry, in the aviation sector, in the automobile sector, in our mobile phones, in each and everything that we are surrounded with today, it contains embedded systems, right? And even in the clouds also. So previously in the clouds we had the software as a service, platform as a service, and um, infrastructure as a service, right? But now with the advent of, okay, this is not now, so now we are in industry 5.0, but previously with advent of industry 4.0, we basically tried to develop this hardware as a service. In hardware as a service, what we did was that we directly deployed our applications into the hardware, right? So along with the software as a service, infrastructure as a service, and platform as a service, now we are getting hardware as a service. And in hardware as a service, one of the key things is deployment of field programmable gate arrays, right? So see what Amazon, the well-known public cloud service providers like Amazon, Microsoft, all these things, they have tried to develop this hardware as a service where they have not only deployed embedded systems but also reconfigurable hardware into that. So in the cloud, what they do is that they deploy hardware, not only normal hardware, but also reconfigurable hardware or field programmable gate arrays. That is, they can be reconfigured, or this hardware can be reconfigured with time. And for this reconfiguration, they need certain bit streams. These are basically the reconfigurable intellectual properties, which essentially configures the FPGA fabric. For different types of applications, there are different types of bit streams, and these bit streams are essentially stored in the cloud repository, right? So in this cloud repository, the bit streams are stored, and based on the user requirement, the bit streams are fetched from the repositories and deployed into the FPGA platforms in the cloud. Okay. And for this, Amazon has developed their EC2 F1 services in AWS. We can easily access them. And also we have this Microsoft Catapult. Okay. So that is available in the Microsoft Azure. So this hardware as a service has become a reality. And over here, what is needed is that what we need to focus is that not only our generic ASIC structures, but also FPGAs, right? Okay, now let me give a brief introduction about the types of hardware that we consider. So the two essential things are field programmable gate arrays, that is the FPGAs, and application specific integrated circuits, that is the ASIC. See, the name will only tell you in ASIC it is application specific, that is once it is programmed it cannot be reconfigured with time. And when it cannot be reconfigured with time, so this makes flexibility or reprogramming a very difficult thing in the present world. Therefore, we have switched to this field programmable gate array. See, the name will only tell you the programmable is given over here. That is, we can program or the reprogram, so the system is quite flexible enough. Okay. Okay.
Participants,
So
please
what are the
mute your
different?
mic. Participants, please mute your mic. 1 minute. Professor, can you unmute? Yeah, please. Dr. Krishnendu, can you unmute, please?
Okay.
Am I
So
audible? Yeah, okay.
yeah. Am I audible?
Yeah.
Okay, great.
Sure. Yeah, please go
So
ahead.
I was here, right? I was here. Okay.
Yes.
So the types of hardware is ASIC and FPGA. So as you can understand from the name only, ASIC tells that it is application specific. That is, once it is programmed, you cannot reconfigure or you cannot reprogram it. So this is not flexible enough, and this flexibility is very important in our present industry 4.0, industry 5.0, right? And for that we need to move to programming in field programmable gate arrays, where see only the name will tell you it is programmable, that is it is flexible, that is we can reprogram with time, right? So what are the differences between FPGAs and ASICs? So there is a comparison. So there is a time to market, FPGAs are fast while ASICs are slow. Then see there is the design, so there is the unit cost, performance, power consumption, unit size. In many places you will find that FPGAs fare better than ASIC, but when it comes to performance, definitely ASICs are quite faster. But FPGAs are with the new FPGAs that are being coming to the market, though it cannot measure the actual thing like ASIC, but still it can be comparable to ASIC performance, right? So these are the things, but essentially FPGAs are much utilized in the current world due to its ability of dynamic partial reconfiguration or DPR, right? So let me give you a basic for FPGA. You know, for in our academics also we try to experiment a lot, and for that, for experimenting with hardware, we definitely seek to FPGA. So firstly, it was used as a prototype, but now it is even being used in deployment in the industry and also in these cloud platforms, right? Okay, so these FPGAs are essentially reprogrammable integrated circuits, which basically contains different types of building blocks or the resources. Okay, so we originally these were popular for prototyping of ASICs, but now also these are used for these high performance computing systems. And moreover, as I told you, that with FPGA there is the dynamic partial reconfiguration or DPR. Okay, so this helps us for scheduling different types of tasks in a spatio-temporal manner. That is, spatio means with respect to space and temporal means with respect to time. So we can basically compute in space as well as time. Okay, so now we have these different logic cells. So these logic cells are essentially lookup tables which basically perform some arbitrary functions based on these small bit width inputs, which can be in the range of 2 to 6, and even with the modern FPGAs this can be more, right? So this can be used for different types of Boolean operations, arithmetic and memory. And along with these LUTs, we have these flip-flops where these acts as some data register, and this can store different types of different types of bits with different clock pulses, right? Okay. Again, we have several DSPs. That is the DSPs are the okay. So DSPs are basically used for different types of multiplication and arithmetic functions, and these are much more faster and more efficient than the LUTs. Okay, and these DSPs are also used for these neural networks, and where these are quite mostly used. So DSPs are essentially the digital signal processing units in an FPGA system. And along with these DSPs, we have different VRAMs, which are essentially small and fast memories. All these VRAMs we have. And there are several other things like the IOs and PCIe interfaces and Ethernet, because you know, with all these new FPGA boards, and we are having the 7 series FPGA boards, all these things can be put over there, and what we have is the entire system on this FPGA thing. Okay, so the present day embedded systems, what is there is that previously what we used was standalone FPGAs, but now we basically put this FPGAs into our SoC platform, and thus we have this eFPGA system, that is an embedded FPGA. You know what happens over here is that we do different types of critical operations in this FPGA portion, and in the rest we do some uncritical operations, right? So these are very common for image processing. You know the face, that's the face needs to be hidden. For the face, for the other things which are not very essential or which are essentially stereotyped, which the operations that does not need to be changed with time, this can be performed in all the other ASIC components, but which are very critical, which needs to be hidden. These are performed in the eFPGA components, okay? And then we have this entire SoC system where we have this FPGA as well as ASIC, we have a software processor, we have several DSP units and everything, and totally we have this embedded system, right? So this embedded system comprises of several things, not only a single FPGA, or this does not only consider of ASIC, but it comprises a mix of FPGA, ASIC, and several software processors, there are PCIe interfaces and all these things, right? Okay, and what do we do in such hardware platforms? Firstly, it is used for acceleration, for hardware acceleration, right? So whatever are the complex time-consuming operations in software, we can definitely execute them in hardware, and it provides a certain level of acceleration, right? And secondly, what we have is that we can perform our different security related operations like cryptographic operations. We can develop our AES crypto code, DES crypto code. We can develop different security related operations over here. Why we do this? The first thing what you know is that there are several types of software attacks, and these software attacks can be nullified if we can directly execute our operations in hardware. So not only we get a hardware acceleration, that is we get a benefit of time, we get a benefit of power, but also we can protect our systems from different types of software attacks, right? And we can do many other things, but what are the secrets over here? Previously the secrets were the cryptographic keys. You know, the cryptographic keys when used in software were associated with a lot of attacks, but when deployed in hardware, several attacks were mitigated. But you know, with time, adversaries also got the better out of it and try to deploy some hardware attacks also, which we will discuss next. And we store these cryptographic keys in hardware, but the adversaries again have found how to exploit the hardware, right? So this we will discuss. But before we move on, let me just give you a thing of what is smart hardware. So we have all these smart applications, right? We have all developed neural network application. We have developed AI or ML applications which have basically deployed several neural networks, and we have got a neural network model, and based on which we have got a smart application, right? So this smart application definitely comprises a neural network, neural architecture such. You know, firstly, if we have to develop something, we need to understand what are the existing things. So we try to find out what are the existing neural architectures and which type of neural architecture will be best suited for our particular application, right? Based on the, so we basically do our neural architecture search, and after we perform a neural architecture search, we select a neural architecture that well suits our particular application. We try to modify that existing neural architecture, right? We try to retrain that architecture. We try to develop some new learning for that architecture. We try to refine. Basically what we try to do is that we try to refine a model. So we have our training data, we have our neural network model, we try to predict what the model can do, and then we try to compare with our targeted output. So if our targeted output is well and fine, then this is good. Or else what we do is we try to find the error in the signal, and then we try to develop a learning or training algorithm which can generate different types of weight modification based on which the neural architecture can be defined. And this process continues until we get close to our targeted output, and finally it ends when we are satisfied with our targeted output, right? Now we have to, now after our smart application is done, what we need to do is that we need to deploy them in the hardware. We need to deploy them in the system on chip, and for that we need to write different types of hardware description language or HDL codes over there. So these HDL codes are basically written in VHDL or Verilog, right? So after we have developed this VHDL or Verilog codes, we try to do all these routing placement and all these things and deploy them in our system on chip. And you know what is the secret over here? The secrets are the weights and the biases that we have obtained, right? Okay, so there is a mechanism of high level synthesis. Definitely the entire thing we do not want to code by hand, right? So if we code by hand, definitely it will be quite time consuming, and therefore the Xilinx and all these things have came up with that HLS for ML. So see over here, the first part is essentially done in software where the usual ML software workflow is there, right? Where you develop the model and all these things, you use all this PyTorch and everything, but then you have to do an HLS conversion. That is the high level synthesis for machine learning. HLS for ML, that is the high level synthesis for machine learning. And the Xilinx gives you a tool for doing this. I am not an expert over here, but definitely those people who does this, they are quite an expert who in converting this machine learning algorithms into this HLS algorithm, right? So some links are given over here. If you want, you can go through the links, okay? And after this, we have what we call is that a VHDL or a Verilog program for the machine learning or the HLS or machine learning or the artificial intelligence or this neural network based architecture that have been developed in software. And after we are happy with the Verilog or the VHDL codes for this AI or ML platforms, we can deploy them into the hardware, right? So before I move on to some of the practical threads, right? So what is the traditional VLSI design flow? So, you know, it all starts with the RTL generation. So over here, after we have developed the idea, we have got the specifications. Now we develop the design architecture. And in this particular case, the design architecture essentially comes from the machine learning or the AI models associated with the neural networks that we have developed in software and converted to a HLS for ML tool into a hardware which essentially contains VHDL or Verilog or the RTL coding. And this RTL coding is essentially some verification is done, then some synthesis is done, then the layout is generated which we pass to the foundry, and then the IC chip is generated. And presently with this machine learning models, we have this intelligent system on chips, right? So this is also an entire design flow where after the design specifications and we get the RTL code, then it moves to the synthesis layout, and then we basically develop the intelligent chips and all these things, right? So what is the present trend of this hardware design? So present trend is that we are focused on outsourcing. So previously, see, we used to do all these things in a single site, but you know what happens is that this is very time consuming, this is very costly, and we need quick time to market deliveries, and also we need cheap products, right? So we have to outsource. So we basically outsource different components into different phases of the VLSI design into different parts of the one. And not only with outsourcing, we also integrate different types of third-party components, different types of third-party intellectual properties into our design, into our chip, right? Now, why we do all these things? So we do all these things firstly to reduce the cost. Secondly, it reduces the expertise required in a single site, right? And finally, it reduces the time to market, okay? So these are quite varied reasons for globalization, and this globalization is followed in today, right? And what is the disadvantage? The disadvantage is that the hardware root of trust is eliminated. So as I told previously, the security is quite important. So with new technologies that we develop, the adversaries try to exploit the new technologies, and believe me, they always get the better of us. They always find out some weak vulnerabilities which they exploit and takes the advantage. And therefore, over here also the hardware root of trust is eliminated. And what are the threats in VLSI design? So the phase can be put in each and every phase of the VLSI design. So I am not going into details over this, but I will be discussing some threats. The first threat that have to be dealt with is the hardware trojans. So hardware trojans are essentially malicious circuits that are put into the ICs that we develop. Okay, so like software trojans, what it does is that it remains dormant during the initial phases of operation, and finally with some after this testing phases is done, or after it has been deployed and some operations takes place, it gets triggered by some internal or external trigger, right? So and then this malicious effects of hardware is exhibited. So where we have a trigger and a payload. A trigger is basically the activation mechanism, and a payload is basically the malicious functionality, right? Which can essentially generate erroneous result or affect the integrity of the system. It can also leak the secret keys of the system, right? And also it can cause denial of service and all these things. So this payload is associated with all these malicious functionalities. Next, we have this counterfeiting. So what is a counterfeit? A counterfeit is simply a fake IP or an IP that do not meet their specifications or do not perform as required standards. So you know what what is the main problem over here? The main problem is the real-time systems. The real-time systems are associated with some deadlines. And if we use this fake IPs, and if this fake IPs does not meet their specification, it causes a certain amount of delay for executing their operations. And if this delay is associated with these operations at real time, then what will happen? It will basically jeopardize our mission critical applications, right? So this unauthorized production of wafers also involves overproduction out of the space, defective parts, cloned ICs, and recycled IPs. And these are essentially the fake IPs that move into the e-supply chain, and these affect the real-time systems. And then we have this IC recycling process. So you know, we all use these electronic gadgets. So we are all surrounded by electronic gadgets, and mostly these are like use and throw types of elements, right? So we have our recycling center. So when we throw off, you know, all our ICs does not go bad. So only like a single, some ICs gets affected, some ICs goes bad, and due to which our entire system do not work properly. But what we do is that we just throw away the entire device, and these devices are moved. These electronic devices move to a recycling center where these PCBs are taken off the electronic components, and those ICs that are still working functionally are selected. These are refined, and these are resold anew. But the problem is when these are resold as new and these are deployed in different types of critical applications, then their lifetime does not match with the actual lifetime. And when their lifetime does not match, then they may stop functioning. And if it is associated with some critical operation, then the effects is quite dangerous, right? So see, this is a vulnerabilities of the e-supply chain, and this is quite well known that the vulnerabilities does not focus on a single stage, but in all stages, from the design stage, fabrication, assembly, distribution, lifetime, end of the life recycling. Okay, so all these pictures I have taken from the internet and from you know, these are easily available in the internet, and you can also get this information from any of the good websites in the internet. Okay, so this picture gives you a good view of what are the vulnerabilities in different stages of the design of an IC, right? Now, what is the key objective? Our key objective is to protect the IP, protect the assets, and protect the supply chain. Okay, so now let me discuss some what are the threats on smart hardware. So like we have developed a neural network based application, right? For a smart application, what the designers do, the designers either generate a custom AI or ML model or use a standard AI or ML model. But this AI or ML model is associated with training on different types of data sets, therefore it has different weights and biases as per the application, right? Now, for the standard neural networks, so these are basically some types of standard neural networks that is chosen. But the important thing over here is that the standard neural networks are basically trained and retrained and different weights and biases are there. And significant time, money, effort is generated in this for the training, for the learning, for the evaluation and all these things, right? So the weights and biases that are associated are quite secret, and with which if you also use a existing neural network model but with the new weights and biases, this becomes intellectual properties. And definitely if you have developed some custom generated AI or ML model, definitely that is an intellectual property by its own. But also if you have used some available neural network and you have trained them for some particular application, then also the weights and bias are different, and therefore this is also a new type of intellectual property that you have created, and which is basically quite confidential and is also quite costly, because you have put a certain amount of time, you have put a certain amount of effort, you have put a certain amount of money for that evaluating, training, learning and all these things, right? Now, what are the goals of the adversary? The goals of the adversary are like the previous one, that is, it will try to steal the model, it will try to steal the weights and biases of the model, and it will try to reverse engineer and recreate the model, right? And what it will cause? Firstly, it will try to affect the system integrity by generating erroneous result, or it will cause the model to malfunction. So the second type of attack that it can cause is on the system's confidentiality, where different types of power analysis, timing analysis. It will try to understand or try to capture the number of memory reads and writes, and based on this power, time, memory reads and writes, it basically tries to duplicate a neural network architecture. Okay, so this type of attacks is quite common in today. Now it will also attack on the system integrity, and in the system integrity, the quite famous attack that happens is the row hammer attack. So what is row hammer? Row hammer, what happens over here is that in row hammer attacks, some some read operations are performed in constant frequency in one memory row, that basically changes or basically causes bit flips in its adjoint memories. So what happens over here is that in FPGAs can be dynamically partitioned into different portions, and these are allocated to different users, right? So in this cloud, these are effectively used. Okay, so what happens is that the users are allocated different rows in the DRAM, local DRAM. Okay, and if a malicious user basically causes certain read operations at a particular frequency, then it can cause some bit changes to the memory spaces that are allocated to some another genuine user. And if the bit flips occurs in the memory spaces of a genuine user, then what will happen? It will the operations that will be associated with reading of the data in the memory will get affected, and the results will be erroneous. So row hammer attacks is quite important in today, and it will affect the system integrity. Why it will affect the system integrity? The reason is that the FPGAs or the hardware does not have so much of resources, right? And to deploy all these neural architectures into the hardware, we need some compression techniques, we need some quantization, and we need some parallelization. And in this, what we do is that we definitely deploy them in hardware, but in this phase, the accuracy gets affected. And different real-time applications are associated with precision of the system, with accuracy of the system. And when we try to do this, we try to compress, we try to quantize, we try to parallelize. This affects the accuracy of the system, right? So what can be the solutions? Firstly, the solution is that we can obfuscate the hardware, and when we obfuscate the hardware, we basically alter the runtime traces, and we basically alter the timings. We try to synchronize the timing, or we try to confuse the attacker by by mixing up the timing, and this altering the runtime traces will basically mitigate this type of attacks. Okay. Secondly, we try to mitigate the timing algorithms via some genetic algorithms. Okay. So this type of things are also taking into place, where we are using genetic algorithms to mitigate the timing differences. And in this, what happens, we try to predict with time that, okay, these are the operations, we have done this, and how we can do this in future. Okay, so with different intelligent algorithms, not only we are doing this obfuscation, we are also trying to mitigate the timing differences, right? And we also try to introduce the noise to the execution traces to prevent some attacks. So if we try to put noise, it basically confuses the attacker, right? And when we try to put the noise over here, the attacker cannot understand the actual signals based on the timing traces. Okay. Finally, we try to do some shuffling of the read or write memories, right? So as you know, this reverse engineering is not only associated with this timing analysis, power analysis, but also they need to understand what type of memory reads or writes have been done. So this memory reads and writes can be basically shuffled, and if we can shuffle up the memory reads and writes, then what will happen is that the attacker will have problems to decipher the original architecture, right? So what we do, okay, this is a work of my own, and this is recently published in IJCNN, which is the International Joint Conference for Neural Networks. So this work I have done in University of Florida when I was a postdoctoral associate over there. So in this, what we try to do is that we try to prevent the accuracy of the system from getting destroyed. So how we do this, we try to find out how much are the unutilized memory blocks, or what are the VRAM spaces that are unutilized in the memory, and we try to organize the memory in such a manner. We try to basically categorize which functions are associated with more accuracy, which functions are associated with more precision, which functions needs more amount of power, which functions needs more amount of time, and based on this we try to find out list, and then we map them into the memory so that the accuracy of the system can be restored. And this also not only ensures accuracy, this methodology also ensures reduction in resource latency and power. So this was one of our works which I have done over there. So we have designed the architecture into several layers of logic computation and memory access, and we have designed the memory blocks in such a manner that the accuracy can be prevented from getting destroyed, right? And finally, this is a self-aware approach. The self-aware approach I have been doing throughout my PhD. But this self-aware approach for neural network things is being recently done, and this is affected in quite a big conference in Europe. That is the IEEE, the Digital Fault Technologies Conference in 2023. So this is accepted. So in this work, what we do is that, as I have told you previously, we need to focus in security not only from the local perspective, but also from the global perspective in a distributed model, in a distributed system. So when it comes to hardware, we basically develop different types of hardware agents that basically works on the observe, decide, and act. So they observe, they decide, they act, and finally they come to a decision. This decision they sends to other agents, and they collaborate among themselves and tries to develop some cognitive based decision making. So this global decision is also important, and for this security at the local level with this local hardware agents is important, and these hardware agents are also used for preventing different types of row hammer attacks. Okay, so
Correct.
to conclude, what we can
Yeah.
say is that it is better we need to understand what security means for AI or learning systems, and we also need to detect what a learning system has been, whether a learning system is basically fooled or compromised, right? So we need to build a more resilient system that guarantees that have strong guarantees, right? So we need to mitigate the misuse of AI. So I have discussed in this talk that how AI can be misused in today's world, and we need to mitigate the misuse and what should be the right policy. So this policy making should be important. And with today, with industry 4.0, with industry 5.0, we have come a long way from software. We have came to deploy the smart neural network based applications on hardware, right? And when we are trying to deploy on it, our focus on security and all these things must also be associated with hardware and not only on software. Okay, so this is where I will end the talk, and really thank you for attending this. So I think we have 5 minutes or something for some questions. So I am ready to take the questions.
Thank you, Dr. Krishnendu. A very,
Yeah.
very good coverage and good sessions in AI and ML and applications. Yeah, and yeah, our participants, if you have any queries, please write down in chat box or otherwise you just unmute and ask, and use this session to interact with the speaker and ask your doubts.
Okay, so what I will say is that I know that at this moment it may not be possible for everybody to ask questions, but I am definitely there. I have given my email, and I am definitely there. So if anybody has some problems or something at any time, so they are free to email me, right? And I'll be giving them the responses.
Okay. Okay. Thank you, sir. I think time is also we are considering. Yeah. Uh, Thanks a lot, sir, for on behalf of Amrita Vishwavidyapeetham and School of AI. And I want to thank you for your presence. And I want to wholeheartedly thank you for appreciate your clearance and support for our department too. Thank you. Thanks a lot, sir. And thank you for all
Okay,
participants for
thanks.
the venturing. Yeah, thank you.
Thanks. Yeah.
Take
Bye.
care. Bye. 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 We will keep in touch with you. Bye bye. Yeah.